Friends, welcome to the session, continuation of steady state analysis of type A chopper with RLE load. Okay, I given what is the expression for I of t if the switch is conducting. What is the expression for freewheeling diode? What is the expression for I of t if the freewheeling diode is conducting? Okay, these two equations you know. You tell me. At t equal to t on, yes, concentrate. At t equal to t on, current is reaches to maximum value. Tell at t equal to t on, I of t equal to I max. At I equal to I max, current is reaches to maximum value when it is on state. Then you replace here, substitute in equation 1. This is substitute here. Then what is I max equal to? This is from equation 1. I max equal to Vs minus E by R into 1 minus E power minus R by L into T is T on, plus I minima E power minus R by L into T on. That this is equation 3. This from equation 1 I written. Similarly, at t equal to t of, or at t equal to t dash equal to t of you take. If this time is reaches to t of time, then current is reaches to minimum value. Then from equation 2, how we can write? Then I minimum at t equal to t dash, I of t dash equal to I minima. Then what is I minima equal to? Minus E by R into 1 minus E power minus R by L into T R, plus I maxima, this I am replacing, plus I max into E power minus R by L into T R. Let this is equation 4. Okay. This is I minima in terms of I max. This is I maxima in terms of I minima. Okay. Tell. Now substitute I minima in this equation. You get total equation in terms of I max. Then you get expression for I maxima. Substitute I maxima in this equation. Then you get total expression in terms of I minima. Then you can solve for I minima. Directly I am writing by solving equation 3 and 4. By solving equation 3 and 4, then what is I max equal to? I max equal to Vs by R into 1 minus E power minus T on by Ta by 1 minus E power minus T by Ta minus E by R. This is expression for I max. with respect to RL. What is TA here? TA is taken as L by R. Take TA equal to L by simplifying that and take TA equal to L by R, we can get this one. Then I minima equal to the value of I minima equal to, by simplifying that, Vs by R into e power Ton by Ta minus 1 by e power T by Ta minus 1 minus T by R. This I minimum. This is expression for I maximum and I minimum by using steady state analysis of type A chopper where Ta is L by R. Okay, this is one expression. This is important. Can expect the problems from this formula also if it is given type A chopper. That you can't. Now, yes, descriptive point of view, these formulas are important. Okay, that you can't. And this derivation is also important in IS descriptive, not for gate point of view, but for concept point of view, I am giving this derivation also. But solution you do, this is substitute here, that is simplification is, it's very simple. But this derivation is asking in IS descriptive point of view, even 10 marks, 12 marks or 15 marks also important. That you can't. This I maxima and I minima expressions. By doing the steady state analysis of type A chopper, we are calculated I maxima and I minima. Once you know the I maxima and I minima, then you write a different expression. I maxima equal to Vs by R into 1 minus e power minus Ton by Ta by 1 minus e power minus T by Ta minus E by R. What is I minima? I minima equal to Vs by R into 1 minus e power, right, 1 minus e power minus, yes, what is I minima? E power T by Ta minus 1 by e power minus Ton by Ta minus 1 by, sorry, what that I written? Yes, e power Ton by Ta minus 1 by e power T by Ta minus 1 minus E by R. This is I. This is I maxima expression and this is I minima expression. Once you know the I maxima and I minima, you can write peak to peak ripple current. Peak to peak ripple current in the load. Peak to peak ripple current. Ripple current. Then how to write peak to peak ripple current is also called current excursion. Another name is, it is also called current excursion, denoted by delta I. Peak to peak ripple current or current excursion, delta I. Then how to write delta I equal to? Then delta I equal to maximum value minus minimum value. Maxima minus minimum. You know expression for maximum value, you know expression for minimum value, that you substitute here. Then what you get, you tell me. By substituting maxima and minima. Yes. By substituting maximum value and minimum value of current, then delta I equal to, then I am simplifying this, substitute and simplify, then final expression I am writing. We get Vs by R into 1 minus e power minus d into T by TA. Yes. Then 1 minus e power minus 1 minus d into T by TA. By simplifying and writing T on by T equal to D, this is D is the duty cycle, by 1 minus e power minus T by TA. This is the expression for peak to peak ripple current, delta I. For RLE load, for the peak to peak ripple current, S delta I equal to Vs by R into 1 minus e power minus d into T by TA, 1 minus e power minus of 1 minus d into T by TA by 1 minus e power minus T by TA. This is a peak to peak ripple current. Yes. Now tell me, these ripple currents are maximum at a duty cycle of dash. If it is asked, that this is equation 5. That equation 3, equation 4. Take this is equation 5, and this is equation 6, and this you take equation 7. This is a ripple current. Then ripple currents are maximum at a duty cycle of. Then ripples are maximum at a duty cycle of. Ripples are maximum at a duty cycle of. Then how you can get d delta I by dd equal to 0. You differentiate this and equate to 0. Then if you differentiate and equate to 0, then we can get the condition directly. I am writing. Then at a duty cycle of 0.5, ripples are maximum. You differentiate, apply U by V rule. Actually it is a constant. Then UV rule you can apply. Then you can get at a duty cycle of 0.5, ripples are maximum. Ripples are maximum at a duty cycle of 0.5. Then one more point to remember. Yes, ripples are maximum at a duty cycle of 0.5. Then you want to get the expression for maximum ripple current. Okay, you want to get the expression for maximum ripple current. Then how to get the expression for maximum ripple current? To get the expression for maximum ripple current, substitute d equal to 0.5 in the ripple current equation. Then what is the maximum ripple current? The maximum value of ripple current equal to what we get, and substitute d equal to 0.5 in this equation. Assume that T by TA equal to x. Then what we get? Vs by R into 1 minus e power minus 0.5x into 1 minus e power minus 0.5x. I am substituting d equal to 0.5. Okay, this is maximum value of ripple current. Then 1 minus e power minus x. What is x here? I take an x equal to T by TA. T by TA is taken as a x. Then you simplify this one. What is the maximum value of ripple current? Delta Im equal to, the maximum ripple current, delta Im equal to Vs by R into 1 minus e power minus 0.5x into 1 minus e power minus 0.5x by, how to write 1 minus, this is 1 minus e power minus x, 1 plus e power minus 0.5x into 1 minus e power minus 0.5. Okay, then these two cancel. Then what you get? The maximum ripple current. One of the expression for maximum value of ripple current equal to Vs by R into 1 minus e power minus 0.5x by 1 plus e power minus 0.5. This is one expression. This is the maximum value of ripple current. The point to remember, this delta Im by Vs by R, delta Im by Vs by R is called per unit ripple current. How to define per unit ripple current? This is called per unit ripple current. Delta Im by Vs by R, this is called per unit ripple current. Okay, then I want to simplify this. Shall we write this is in as a trigonometric formula? How to write this one? 1 minus e power minus 0.5x by 1 plus e power minus 0.5. 1 minus, just like 1 minus e power minus 2x by 1 plus e power minus 2x. What that formula? Tan hx. Okay. Then what is the formula for 1 minus e power minus 0.5x by? Then what is the maximum value of ripple current equal to Vs by R into tan hx by 4. Tan hx by 4. Okay. Then maximum value of ripple current equal to tan hx by 4. But what is the x you taken? T by Ta. That you substitute here. What you get? The maximum ripple current equal to Vs by R into tan h of this. What I given? X is T by Ta, you write. Tan xx by 4, T by 4 Ta. But what is Ta? L by R. Then maximum value of ripple current equal to Vs by R into tan h of T is written as 1 by F, 1 by 4F, L by R. Then by simplifying this, what you get, you tell me. Then maximum ripple current equal to Vs by R into tan h of R by 4F. R by 4F. This is the maximum value of ripple current. This is one more expression for maximum value of ripple current. Tan h of R, hyperbolic function, R by 4FL. But you know that 4FL is very much greater than R because we are operating high switching frequency. If 4FL is very much greater than R means tan h of R by 4FL is nearly equal to R by 4FL. This is for approximate. For approximate. I am explaining for approximate. This is exact. This formula is also exact. And this also exact value of maximum ripple current. Exact value of. If R by 4FL is nearly equal to RFL, then what the maximum value of ripple current we can get? Maximum ripple current equal to Vs by R into R by 4FL. Then RR cancelled. Then maximum ripple current delta M equal to Vs by 4FL. This is approximate value of maximum ripple current. Approximate. The approximate value of maximum ripple current. In the case of type A chopper, Vs by 4FL. This one expression you remember, and this also you remember, and this also. Quick note. Over. This approximate value of maximum ripple current. This is exact value of ripple current. Okay. Now from this, I want to write some observations. You'll see here. Yes. It's over now. That you write as a note. That is, ripples are maximum at a duty cycle of 0.5. Ripples are maximum at a duty cycle of 0.5 at D equal to 0.5. It is similar to that what I discussed in buck regulator also, where the ripples are maximum at D equal to 0.5. That's why type A chopper is also called step down chopper. Here also we are getting same condition. Ripples are maximum at duty cycle of 0.5. Then what is the maximum value of ripple current? The maximum ripple current delta M equal to, this is approximate value, Vs by R into Vs by 4FL. The approximate value of maximum ripple current equal to Vs by 4FL. Then if you draw the characteristics here with respect to duty cycle versus ripple current, with respect to duty cycle versus ripple current, if you draw the characteristics, then we get the characteristics like this. Okay, at D equal to 0.5, ripples are maximum. This is duty cycle. This is duty cycle equal to 1. Then what is the maximum value of this ripple current? This delta I am writing. This is Vs by 4Fl. That is, one observation is for 0 less than D less than 0.5. For 0 to 0.5, if the duty cycle is increases, ripples also increases. Important observation. That is, for 0 less than D less than 0.5, if duty cycle is increases, ripples also increase. Yes. Now see, for 0.5 to D, for 0.5 to 1, for 0.5 less than D less than 1, for 0.5 less than D less than 1, if duty cycle is increases, ripples are reduced. Duty cycle is increases, ripples are reduced. Peak to peak ripple currents are reduced. That is one more observation. What is the maximum value of ripple current? Therefore, if inductance is increases, or the maximum ripple current is also reduced. That's why by connecting the large inductor in the load, we can reduce the ripples in the load current. That is, if the inductance is increases, ripples are reduced. Now the question is, one more observation. If the frequency is increases, what the ripples is also reduced. Hence, the observation is, without increasing inductance, in order to reduce the ripples in the load current, we must operate the chopper at a high frequency. That is, without increasing inductance, okay, without increasing inductance. To reduce ripples, that is, chopper must be operated to reduce ripple. Chopper must be operated at high frequency. Chopper must be operated at high frequency. This is one observation. That means by increasing the frequencies also, ripples are reduced. That's why if you want to reduce the ripples without increasing the inductance, the another way is we must operate the chopper at a high frequency. Okay, that is another observation. See the one more observation here. We know that what is delta I given? Delta I equal to Vs by R into 1 minus e power minus d into t by Ta into, this is delta I expression I given, delta I into 1 minus e power minus 1 minus d into t by Ta. Okay, by 1 minus e power minus t by Ta. This expression you know. Now from this, what is delta I by Vs by R? Delta I by Vs by R is per unit ripple current. This is called per unit ripple current. Listen please. For example, if D equal to 0.5 and T by Ta equal to 5 you take, then we can get the per unit ripple current is nearly equal to 0.85 amperes we can get. Nearly. This you substitute here, then we get nearly equal to 0.85 amperes. If you substitute D equal to 0.5 and you take T by Ta equal to 25, then you get per unit ripple current is nearly equal to 1 you can get. This is per unit ripple current. I'm talking about per unit ripple. Then if you take, then what is the per unit ripple current you can get? The per unit ripple current is nearly equal to 1 ampere per unit na. Yes, delta I by Vs by R. Per unit ripple is 0.85. Per unit ripple is 1 per unit. Like this. That means if T by TA is increases, if T by TA is increases, what the per unit ripple is also? Per unit ripple is also increase. Per unit ripple is also increase. If T by TA is increases, per unit ripple is also. Then if you draw the characteristics between, per unit ripple and different values of T by TA. If you draw the characteristics between per unit ripple, here per unit ripple and different values of T by TA. Per unit ripple. And you taken this is duty cycle. This you taken duty cycle. Let this is D equal to 0.5. For different values of T by TA, then if you draw the characteristics, what you can get? Then we can expect the characteristics like this. Ripples are maximum at D equal to 0.5. This is for T by TA equal to 5. This is for T by TA equal to 25. This per unit ripple is 1. This per unit ripple maximum, this per unit ripple is how much? 0.85. Let for different values of, this is for different values of T by TA. Yeah. Then ripples are maximum at D equal to 0.5. For any value of T by TA you take, ripples are maximum at duty cycle equal to 0.5 only. But if T by TA is increases, what about the per unit ripple is also increased. Then what is TA? TA is nothing but a L by R. TA is nothing but a L by R. But point to remember, if TA is nothing but L by R, if L is increases, what is TA? TA is increases. If TA increases, what is T by TA? Reduces. If T by TA is reduces, or the per unit ripple reduces. That's why by increasing the inductance, you can reduce the ripple. This is another proof. By increasing the inductance, we can reduce the ripple. Clear? That concept. Different observation. Quick, note down. This duty cycle equal to 1. To T by TA and D is 0.5, you get this nearly equal to this. T by TA 25, D equal to 0.5 here, then you can get nearly equal to 1. Yes. Now, we want to analyze this circuit under boundary condition also. Same concept I discussed already even in the buck regulator also. Here at the boundary condition, what is the duty cycle you want to calculate. Okay. Then in a type, this is a continuation of steady state analysis of type A Chopper1. All this concept is steady state analysis with respect to type A Chopper1. Okay. Now we'll see duty cycle at boundary condition. In type A Chopper, duty cycle at boundary condition. Yes. Duty cycle at boundary condition. In type A Chopper, duty cycle at boundary. at boundary condition. At boundary means just to continue. At just to continue. At boundary condition means at just to continue. At just to continue. Okay. We know that so many times this concept I given in the regulators also. At just continuous, what is the minimum current equal to 0? I minima equal to 0. This waveform at just continuous. Then which current is 0? This is I max. This is T. Okay. This is at just continuous minimum current equal to 0. What is the minimum current expression in the case of type A chopper? Vs by R into, then what is the minimum? I minima equal to Vs by R into e power T on by Ta minus 1 by S. E power, this is e power T by Ta minus 1 minus E by R equal to 0. Shall you write like this? Then e power T on by Ta minus 1 by e power T by Ta minus 1 equal to E by R. Let this is into Vs by R. No? This I minima, this is expression. This is Vs by R minus E by R, that is equal to Vs. This is Vs by R. This R cancel. Then from this what you can write? E power T on by Ta minus 1 by E power T by Ta minus 1 equal to, what do you get? This E by Vs. Let this E by Vs equal to M. Then this E by Vs equal to M means, from this how we can write? Therefore, E power T on by Ta minus 1 equal to M into E power T by Ta minus 1. Okay. This I am assuming that E by Vs is M, where M is E by Vs. Okay. Here I taken M equal to E by Vs. Then E power T on by Ta minus 1 equal to, you bring this 1 into this side, 1 plus M into E power T by Ta minus 1. Okay. Now from this, take natural logarithm on both sides. T on by Ta equal to ln of 1 plus M into E power T by Ta minus 1. Then what is T on equal to? Ta into ln of 1 plus M into ln of 1 plus M into E power T by Ta minus 1. Okay. Then from this, T on is written as a dt. T on is written as a dt. Then you bring this dt equal to Ta into ln of 1 plus M into E power T by Ta minus 1. Then from this, what is d equal to Ta by T into ln of 1 plus M into E power T by Ta minus 1. This is, that this duty cycle is taken as this is D, but I taken this is D dash. I take this is D dash. Okay. This is duty cycle at boundary condition. Duty cycle at boundary condition. At a boundary condition. This is the minimum duty cycle to make the current is just to continue. For RLE load is given in a type A chopper, what is the minimum duty cycle to make the current is just continuous? D dash equal TA by T into ln of 1 plus m into e power T by TA minus 1. This also is. This is a minimum duty cycle to make the current is just continuous. If given duty cycle, if any duty cycle is given, if given duty cycle is D, then if given duty cycle is D greater than D dash, then it is continuous mode. I'm explaining this type A chopper conditions for continuous mode and discontinuous mode. If D less than D dash, then this is discontinuous mode. If D equal to D dash, then it is just to continue. Okay, this conditions you remember. If D greater than D dash, it is a continuous mode. If D less than D dash, discontinuous mode. If D equal to D dash, it is a just to continue. This is the duty cycle at what condition? This is the duty cycle at just to continuous at boundary condition. This is okay, no doubt. Yes. Still, continuation of this type A chopper is also still some concepts with respect to steady state analysis of type A chopper is there. That will continue in the next session. Okay. Still some concepts are there based on this one. Then if type A chopper is operated in discontinuous mode, how to write the formula? If it is operated in discontinuous mode, how to write the formula? And if it is operated in continuous mode, whatever the output voltage we are getting, then that is not a constant DC, it is a pulsating DC. If it is a pulsating DC, then how to apply the Fourier analysis? These two concepts I want to discuss, and along with some observations also I want to write. With that, the theory with respect to steady state analysis of type A chopper will be completed. And after that, based on the quadrant operation of chopper, we can solve some classroom work questions. Okay, so we will continue in the next session. Thank you.